Hi, I'm Ashlin. I'm a PhD student at Newcastle University. I work with Dr. Tamara Rogers, along with our team of postdoc researchers, Dr. Ratish Ratnasingham, who did all the 2D simulations presented in this work, Dr. Ricardo Vannon, and Dr. Philip Edelman. And today I'll be presenting our work on chemical mixing by internal gravity waves in stars. So as Corinne already explained in very detail, mixing plays a major role in stellar evolution, particularly in massive stars, where they bring in more fuel into the core, thereby increasing the main sequence lifetime and also affecting the later stages of stellar evolution. Mixing also causes elements to move towards the surface, creating abundance radiations and modifying the surface abundances. So such studies suggest different mixing mechanisms at the convective radiative interface, as well as in the radiation zone. So in this talk, I'll be focusing on the mixing by internal gravity waves in the radiation zone. So about these waves, these are waves with gravity as the restoring force, and they propagate in a stably stratified region. We find these waves in the atmosphere, for example, when wind flows over a mountain, or in oceans, where they are responsible for the turbulent mixing. In stars, any disturbance in the convection zone can generate these waves. So the movie here, it shows the convection zone at the top with the waves generated from the convective radiative interface, propagating into the stably stratified radiation zone. So as these waves propagate, the amplitude is affected by a number of factors, among which density is the most dominant one. And therefore, these waves have different effect in stars with different masses, as they'll be propagating into a region of increasing density in low mass stars, whereas they'll be propagating into a region of decreasing density in massive stars. So by massive star, here I mean stars with the convective core and a radiative envelope. So all the models that we have studied in this work have the configuration of a massive star. So with these models, we studied the mixing by internal gravity waves by conducting numerical simulation to solve the 2D hydrodynamic equations, the conservation of mass, momentum, and energy in the inelastic approximation. So we filtered out the sound waves and including the effect of density stratification by considering an equatorial slice of a star. So the models presented in this work consider no rotation, and the thermal and viscous diffusivity, it's maintained constant throughout the simulation domain. So we have a background reference state model taken from the 1D stellar evolution called NISA. And from our numerical simulation, we calculated the velocity over a time. Now to study mixing, we introduced tracer particles into our simulation, and we tracked the trajectories of these particles. Before looking into the mixing profile, we wanted to see if these particle motion behave like diffusion. So for that, we introduced particles at 3 different radii, R1 in the convection zone, R2 and R3 in the radiation zone. So as we know, the mixing would be well efficient in the convection zone in a very short time scale. To see what happens in the radiation zone, here is a movie which shows that the particles are mixed well by the waves. So here we track the trajectories of each of these particles, and we calculated the mean square displacement. So the plot on the right, it shows the mean square displacement in the y-axis, plotted as a function of time differences in the x-axis. So here, the time difference, each time difference has the contribution from all the time steps that we considered in the simulation. So the amount of contribution, it decreases as we move to the higher values. And this is represented with the dark blue having the maximum contribution to the time difference, and the lightest blue having the fewest contribution. So as it is evident here, the mean square displacement is a linear function of time differences, therefore telling us that the mixing by internal gravity waves can be treated as a diffusive process. We also note that the slope varies, increases as we move from R2 to R3, which suggests that the mixing is stronger as we go towards the outer radii, as it's evident from the movie here. So now we introduced a number of particles into our simulation, and we calculated the diffusion coefficient at each radii. So the plot here, it shows the diffusion coefficient in the units of centimeter square per second, plotted in the y-axis, against the radius in centimeter in the x-axis for different sets of particles given in different colors. So as you can see here, the profile follows the same trend for all the set of particles, that is, it's increasing from the convective radiative interface, which is shown here as by the vertical dashed line towards the surface. So we see that the diffusion profile is already converged for 10,000 particles, and we use this particle resolution for all our further analysis. And apart from the particle resolution, we varied various other parameters in our simulation, such as the radial grid size and the time resolution. And in all the cases, we saw that the profile followed the same trend. That's an increasing trend towards the surface that led us to the conclusion that the radial diffusion profile is robust. So now we got a mixing profile. We wanted to see what sets this mixing profile. Rogers and McElveen had found that the diffusion profile is set by the wave amplitude, and they approximated the diffusion coefficient with the following equation, here where A is a constant, and we calculated the wave amplitude using the linear theory from Ratnasingam et al., where the wave amplitude for each frequency omega and wave number L depends on the wave driving, the density stratification, the geometry of the star, the Brand-Weisser frequency, and the radiative damping. So here R0 is the initial reference point at which the waves are launched, and ρ0 and n0 are the corresponding initial density and Brand-Weisser frequency. The damping coefficient we calculated using the following equation from Kumar et al., where the damping coefficient varies directly with the wave number and Brand-Weisser frequency and inversely to the frequency. So using these equations, we calculated the theoretical diffusion coefficient for a set of frequencies and wave numbers. And we found that we considered the wave for a wave number L equal to 1 because the contributions from higher wave numbers were negligible as expected from this equation. So the plot here, it shows the diffusion coefficient plotted against the radii for a 7 solar mass 0 age mean sequence star. With the blue, the diffusion profile obtained from the simulation, and in pink, the theoretical diffusion coefficient calculated using this equation for a 5 microhertz wave, which provides the best fit to the profile from the simulation. So as you can see, the theory agrees well with that of the simulation, and therefore this can be used as a simple prescription for including mixing in 1D stellar evolution models such as MESA. So overall, we see that the profile follows an increasing trend towards the surface, but as the star ages, the structure changes, and from this equation, we would expect the diffusion coefficient to vary. So to find that, we extended our analysis to models of different masses and across different ages. So here is the profile variation with mass. The plot here shows the diffusion coefficient in the y-axis, plotted against the radius in the x-axis at 0 age mean sequence for the different masses. Given in black is for a 3 solar mass model, in red is 7 solar mass, and in blue it's 20 solar mass, with the vertical dashed line indicating the convective radiative interfaces for each models. So as you can see here, the profile follows the same trend for all the models. That is, it increases from the convective radiative interface towards the surface. So here the dominant factors contributing to this mixing profile, it's the density stratification, which amplifies the wave as it moves outwards, and the thermal damping, which modulates the density stratification by damping the waves in the radiation zone. We also see that the mixing is stronger for the 20 solar mass model compared to that of a 3 solar mass model. And this can be explained by the stronger convective driving in massive star than that of a low mass star. And there is another factor, it's the Brand-Weisser frequency. So the lower Brand-Weisser frequency for more massive star leads to lower damping, contributing to the stronger mixing that we see in the high mass star. So here is how the profile varies with age. So the plot here, it shows the radial diffusion profile for a 7 solar mass model with the 0 age mean sequence represented by the solid line, mid mean sequence represented by the dot dashed line, and the terminal age mean sequence given in dotted line. So as you can see here, the profile varies significantly as we move from SAMS to the TAMS model. So this considerable difference in the diffusion profile for the TAMS model, this can be explained using the following equation here. So the second order differential equation, we obtain this by reducing the linearized two-dimensional hydrodynamic equation. So given here in purple, it's the oscillatory term, and in green, it's the density term or the damping term. So in the radiation zone of a star, there are regions in which the oscillatory term is dominant and some other regions where the density term is dominant. So here we consider the ratio of the oscillatory term to the density term to determine what's known as the turning point, which is the approximate radius at which this ratio is equal to 1. So the plot here, it shows the ratio of the oscillatory term to the density term plotted against the fractional radii. For the SAMS models, it's given here in black, the BDMS given in red, and TAMS given in blue. So what happens at the turning point is that the waves lose their wave-like behavior, and therefore it experiences extra damping. So as you can see here from the plot, in older stars, the density term, it dominates towards the surface, and therefore it causes extra damping. And we can see here the effect of the turning point on the diffusion profile, where the vertical lines given in black, red, and blue corresponds to the turning point shown in the plot on the left. So as you can see here, in SAMS and mid-MS, the turning point has no or very little effect on the mixing profile. Whereas if you look at the TAMS model, the turning point, it approximately coincides with the radius at which the diffusion profile starts to show the decreasing trend. So as these waves approach the turning point, the wave loses their wave-like behavior and it becomes evanescent, causing the decreasing trend in the mixing profiles in TAMS. So in general, can say that the profile varies significantly as we move from the younger star to the older stars. So along with density stratification and the thermal damping, the Dunn-Weisseler frequency is also more prominent in the older stars. The Dunn-Weisseler frequency spike near the convective radiative interface, it traps the waves, thereby resulting in a fewer contribution to the mixing profile, which also results in the decreasing trend as we see here. So now we got the mixing profiles across different ages and masses from the simulation. We extended our theoretical calculations across all the models, and we found that the linear theory agrees well with all the SAMS and mid-MS models, with the dominant frequencies contributing to this mixing profile in the range of 3 to 9 microhertz. So here is a plot showing the diffusion profile from the simulation for a 7 solar mass mid-MS model given in blue, and the theoretical diffusion coefficient corresponding to 4 microhertz in pink. So as you can see here, the theory agrees well with that of the simulation. And they also found that the dominant frequencies were lower for more massive stars. We also looked at how the theoretical diffusion coefficient vary for TAMS model, and we find that the theory couldn't explain well. So here is an example showing the diffusion profile for the 7 solar mass TAMS model in blue from the simulation and in pink from the theory. The theory and the simulation doesn't match, as I had already mentioned before. So I conclude my talk here. with the following takeaway, that we found that the mixing is stronger for more massive stars. The mixing changes substantially with age, mainly because of the turning point and the Brandweiss error frequency. We noted that the younger stars have higher mixing, and it reduces markedly with age. And we found that the dominant frequencies contributing to these mixing profiles are between 3 to 9 microhertz. The frequency is decreasing with mass. So thank you for the opportunity to present the talk, and thank you all for the attention.
All right, let's thank the speaker. And that was with 4.5 minutes to spare, which is wonderful. So we have plenty of time for questions. I already see at least one hand.
Thank you. That was a lovely talk. This is Jamie Tyra. I was wondering if you've thought about whether there are any sorts of observations that can confirm the beautiful mass and evolutionary trends that you predict should be there.
About the actually, I don't know. I haven't thought about that.
All right. Awesome. We should talk.
From experience, I know that's a great conversation to have with Jamie. All right, we got several hands up.
Yeah, quick question from the chat from Pascal Garot. There's a question, it's kind of two aspects of the diffusion coefficient. One is how do you pick the coefficient A? I think it's like A times the velocity squared, which I think dimensionally that should have dimensions of a time. And then kind of related to that, do you have a physical interpretation for why the most important waves seem to be around 3 to 9 microhertz?
So about the coefficient A, was determined to be, it was speculated to be equal to 1 by the studies from Rogers and McElwain, and it is assumed to be dependent on the rotation or thermal diffusivities. And about the dominant frequencies, so we found the dominant frequencies to be in the range of 3 to 9. So these are the range of frequencies that are high enough to escape the thermal damping, but low enough to be generated with sufficient amplitude.
All right, thank you.
Hi, Ashlin, it's Dominic here. I was actually going to answer Jamie's question, if I may. So if, and here's put some spice in, to use Daniel's word, if the waves reach the surface, one might imagine that the dominant frequency range decreases with age, and that is exactly what we see. So I think that's encouraging. And also observational evidence one might look for is, for example, the mixing profiles that Mike Pedersen has been modeling. So we're very excited to take prescriptions for mixing and put them into our models to look at an age-dependent mixing parameter.
Thank you. Another question.
Hi, Michael Pilson here. I was just going to add to that. So actually one of my ongoing projects with Ashlin at the moment is to try to take these profiles and put them in MESA and see if we can use gravity modes to distinguish and also have a look at the surface abundances for that. So that's work in progress. We're not there yet, but that was one of my ideas for this program to work on while I'm here. So hopefully soon we'll have some answers for you on that.
Thanks, Mai. I should have mentioned it before.
Hi, this is Adam Germain. Following up on Pascal's question, do you understand why it scales like V wave squared? That's sort of not what I would expect naively, but I'd be interested to know.
So here, the previous studies by Rogers and McElwain, they had found that the diffusion coefficient it varies as the square of the wave amplitude, as it is the wave amplitude is correlated over a longer time. as it is correlated over time, whereas the root mean square velocity is not. So this, since diffusion is related to the time correlation, we would expect the diffusion coefficient to be to vary with wave amplitude.
Okay, thank you.
Hi, Ashlin. This is Jim Fuller. So my question was originally the same as Pascal's about the value of A. And I guess I don't understand. You said it depends on thermal diffusivity, but I don't understand how, or like how it depends on thermal diffusivity. We know it has to have to have the units of time, like Daniel said, but.
So this coefficient was it was actually found by Rogers and McElwain, and they found the value A to be 1 with the units in second. So they assumed that it would depend on thermal diffusivity and rotation and other factors. It's based on their work.
Okay, can you maybe type that citation into the chat? I'd be interested to see it.
Yes, I will do.
Okay, thanks.
I have a question regarding the Paul Kerwick. I have a question regarding the size of the diffusion coefficient that you find. It seems like you have 10 to the 9 for 20 solar mass star in the envelope, and you say that it goes down, but 10 to the 9 centimeters squared per second in the envelope of a 20 solar mass star should lead to very quick, almost instantaneous mixing, and you would have one of these homogeneously mixed stars, I think probably within 10% of the main sequence lifetime. And this is my estimate from doing the cell evolution on my head real quick, but is that something that concerns you, or is that sort of size somehow mitigated by something else? Like I think you would end up with a fully mixed star very quickly with that amount of mixing.
I think it also depends on the simulation domain that we have considered here. So for the 20 solar mass, the simulation domain extends only up to the 80% of the total stellar radii.
I think your answer just now didn't quite come through as clearly as before. Could you repeat that?
Sorry. So I think it might depend on the simulation domain here. So in the 20 solar mass, the simulation domain extends only up to 80% of the total stellar radii.
Hi, this is Ylva Göthberg. Thank you so much, Ashlin, for such a really nice talk. It's really impressive to see this work. My question was very similar to Falk's, but yes. So I wanted to extend the question to, do you think that there is some way that you can damp this wave mixing a little bit, or something like that? Because like a 20 solar mass star, maybe, I mean, if they do get fully mixed, that's very interesting, but I think that there is also 20 solar mass stars that are not fully mixed.
The thermal damping coefficient we have considered, we consider a constant thermal diffusivity across the simulation domain in the simulation. And we also have models with varying thermal diffusivity. So maybe that's something to look into, how the diffusion profile varies with a varying thermal diffusivity towards the surface. So the difference in the diffusion profile, which we obtain from using a constant thermal diffusivity and a varying thermal diffusivity, might be able to say something.
Yeah, how interesting. I look forward to see that. Thank you so much.
Same. That sounds really cool. We got a couple more questions.
Hello, this is Daniel Quene. I know that sometimes some simulations use a boosted luminosity, which I think can drive more waves than normal. Do you know if the simulations that you're running here are using the realistic stellar luminosity, or if it's been boosted for numerical reasons.
I'm actually not sure about the luminosity used, but we used an enhanced thermal diffusivity in the simulation.
Hi, this is Philip. Just to comment on that. As far as I know, with these simulations, what we did is we fixed the super adiabaticity in the core and calibrated it so you get the same VRMS as what MESA predicts from mixing length theory. So the velocity should be what we have in MESA. As far as I know, I think that's what Varghese did in most simulations.
Thank you.
Thank you.
Other questions from the audience?
Question from the chat from Pascal Garot. Is the diffusion coefficient anisotropic? So I guess you could have horizontal diffusion, radial diffusion. Have you looked at that at all?
So we are just looking at the radial diffusion profile here.
Thanks. Also, a question from Corinne Charbonnel. Have you looked at all about differential damping between prograde and retrograde waves? I think this has to do with angular momentum transport, so maybe not the main topic of this work, but if you've looked at this at all.
No, we haven't looked at any of that now. Yeah, we just focused on the chemical mixing by internal gravity waves in here.
I had a quick question, actually. This is Adrian Fraser. Now that you've got this sort of pipeline set up to do these studies, are there any parameter variations that you're looking forward to doing next? Personally, I'm wondering what varying something like the Prandtl number might do, but I was wondering what the next step is.
These models include no rotation, so we're looking into the models by including the rotation.
Oh, I see. Okay, good to know. Other questions from the audience? All right, well, with that, let's thank the speaker.